Hello guys, welcome back to my YouTube channel. So today we are going to solve day 30 problem of this month on LeetCode. Before starting, if you guys haven't subscribed my YouTube channel yet, then please go ahead and subscribe it. Now without any delay, let's get started with today's problem. Problem number 2097, valid arrangement of pairs. Okay, so in this problem you are given a zero indexed 2D integer array pairs, right, where pairs of i's having two values, one is start and one is end, and arrangement of pairs is valid if for every index I, okay, we have the end of I minus 1 is equal to start of I. Okay, so see this pairs. Okay, so here just see the output of this one. So ending is 9, right, and this is the starting of the next one. Ending is 4 and this is the starting of the next one. Ending is 5 and this is the starting of the next one. Okay, that is the simple meaning of this line. We have to return any valid arrangement of pairs. Okay, so in any order, but this condition should be satisfied. Okay, note, the inputs will be generated such that there exists a valid arrangement of pairs. So this is given to us. There always exists a valid arrangement of pairs. Okay, so result is always possible here, right? And these are the constants given to us, right? No two pairs are exactly the same. Okay, and start is not equal to end, right? And there exists a valid arrangement of pairs. Okay, this is important line, this is important line. Okay, all are important only. Okay, so now see this example number 1, right? So here you know what we need to do, right? Output is clear for this particular example. Okay, so we are going to use this Eulerian path. Okay, what is this Eulerian path? So it is a path in a graph that visits every edge exactly once. Okay, and Eulerian circle, a circuit is an Eulerian path that starts and ends on the same vertex. Okay, so see this example. This is graph. Okay, so let's say I'm starting here. Okay, so what is the degree of this one? So here if you see, this is 1. Okay, and here 2 edges from here, so 2. Here 3 edges from this 0, so I'm writing 3. From 1 2 edges, right? 1 here and 1 this, and from this 2, okay, this 2. Okay, so here I am starting from this odd, okay, this one. So I visit this edge, then 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 I visit this edge. Okay, so I have covered all the edges. Okay, the graph has Eulerian path. Okay, for example, it's 4 3 0 1 2 0, but no Eulerian cycle. Okay, why cycle is not there? Because I am starting from this 4 and I am not ending at the same 4 again. Okay, same vertex. So note that there are two vertices with odd degree, 4 and 0. Okay, odd degree. Okay, so here if all the nodes in a undirected graph have an even degree, then the graph has Eulerian circuit, right? So in this graph all the nodes are not having even degree, right? An Eulerian circuit is a closed path that visits every edge exactly once and returns to the starting point. Okay, this is for even degree for all nodes. Now exactly two nodes with odd degree. Okay, so this was the case here, exactly two nodes with odd degree, right? So if exactly two nodes in the graph have an odd degree, the graph has Eulerian path. Okay, graph has an Eulerian path, but not a circuit. And Eulerian path starts at one of the odd degree nodes, starts at one of the odd degree nodes and end at the other odd degree node. Okay, so why this holds true? So in any graph, the sum of all the degrees of nodes is twice the number of edges. Okay, obviously. So let's say this is one graph. Okay, so in this graph, tell me the number of edges. Total number of edges are 3. Okay, and now the sum of degrees. So sum of degree, if you do here, so for this 2, for this 2, for this 2, total 6. 6 is the degree and total number of edges is 3. So yeah, this is valid case, right? Therefore the sum of degrees is always even. If a node has an odd degree, then it contributes an odd number to the sum to keep the total sum even, right? There must be an even number of nodes with odd degree. Okay, hence in an Eulerian path circuit scenario, there are either no odd degree nodes, that simply means Eulerian circuit, and exactly two odd degree nodes, that simply means Eulerian path. Okay, now see this. So here 1 2 1 2 1 2 3 4 1 2 and 2. Okay, so this is even degree, right? So all the values are even, right? So here you can start here, 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 here. Okay, you can do anything, right? And here the graph has Eulerian cycle, right? And here the graph is not Eulerian. Note that there are four vertices with odd degree, odd degree, odd degree, odd degree, odd degree, even degree. Okay, so four vertices are with the odd degree, right? So this is not even a Eulerian. Okay, so this is nothing but our Eulerian path. Okay, so now how I'm going to solve this problem? Okay, so simply I am talking about this Eulerian path and all, so definitely I'm going to use graph only, right? So here uh, this is my example, right? Pairs 5 1. Okay, so let me write it like this: from 5 to 1 there is one edge. Okay, directed graph. Okay, and 4 to 5 there is one edge. 4 to 5 there is one edge. Okay, uh, 11 to 9 there is one edge. 11 to 9 there is one edge. Okay, and then 9 to 4 there is an edge. Okay, 9 to 4 there is an edge. Okay, so now if you just draw it, so here how you are going to draw it. Okay, so 5 to 1 there is one edge. Okay, 4 to 5 there is one edge. Okay, 11 to 9 there is one edge. 11 to 9 there is one edge, and 9 to 4 there is one edge. Okay, so this is how you are going to draw it, right? 9 to 4 there is one edge. Okay, so here this graph is like this. Okay, the arrows. Okay, so here I'm just going to write the in degree and out degree. Okay, so in degree for this one is 0, and out degree is for this one is 1. Okay, so here this is in degree, this is out degree. In degree means number of directed arrows to this 11 node. Okay, no, but from here we are moving to 9, so 1. So this for this 9 1 1. Okay, in degree and out degree both are same. So because there is one edge which is incoming, there is one edge which is outgoing. For this 4 1 1, for this 5 1 1. Okay, and now for this 1. Okay, so we have incoming as 1 and outgoing 0. Okay, so now here by graph, by visually, you know that you are going to start from here. You are going to make one pair this 11 9, then you are going to make one pair of 9 4, then you are going to make one pair of 4 5, then you are going to make one pair of 5 1. Okay, this is nothing but your output, right? 11 9 9 4 4 5 5 1. Okay, so visually you know this, but how you are going to find out that this node is going to be my starting point? Okay, so how you are going to do this? Okay, so that's what we are going to see, how you are going to find out that this my particular vertex, okay, or node is my starting point. Okay, so here what you need to check, so you need to check here outgoing, okay, out degree of any node if it is equal to in degree of node plus 1. Okay, that simply means that is going to be my starting vertex. Okay, so out degree for this one, okay, out degree for this one is 1. Okay, out degree for this node you see is 1, and in degree for this one is 0, and if I add 1 to it I get 1 is equal to 1. Okay, then this is valid, so this condition satisfied for this one. Okay, out degree is equal to in degree plus 1. So if this is the case, I am going to treat that node as my starting. Okay, for others you will see that this condition will not met. Okay, so definitely for my starting node there will be going to be one extra outgoing, okay, out degree node. Okay, so that is why we have to take this condition, out degree is equal to in degree plus 1, right? If this condition is satisfied, then take that. But there may case this condition is not, itself is not there. Let's say there is one cycle. Okay, then it becomes a linear cycle, then you can start from any vertex. Okay, definitely you will get answer. Okay, if this condition is not satisfied and you see that all the degrees, okay, out degrees and in degrees are even only, right? In that case, no problem. Okay, okay, if it is the Eulerian circuit, okay, if it is Eulerian circuit only then. Okay, so only in that case. Okay, but ignore right now, this is not the case. Okay, here, but ignore. Okay, so this is what you need to check. Okay, out degree is equal to in degree plus 1. Okay, so this is one base condition that we need to check, and then we are going to start from here. Okay, so now we know that from 11 I'm going to start. Okay, so what you are going to do, you are going to use post order DFS. Post order DFS simply means that you are going to write the nodes first. Later on, first you are going to visit all the edges. Okay, so here 11 you are going to start. Okay, from 11 you are moving to 9. Okay, so after 9, okay, after 9, just first you are at this 11. Okay, then you are going to move to this 9. Okay, then for 9 you are going to visit this 4. Okay, for this 4 you are going to visit this 5, and for this 5 you are going to visit this 1, and then you are going to see that this one uh, and okay, or we have already visited the childs of this one. Okay, the neighbors of this one, so I'm just going to write 1 first, then I'm going to just do the backtrack. Okay, so 1, then I come to this one from 5, and I come to this 5 from 4, and I come to this 4 from 9, and I come to this 9 from 11. Okay, so first what I'm doing, I'm checking the neighbors, and then for that particular neighbors I'm checking the path. For that particular neighbor I'm checking the path, and once I visit all the edges, I'm going to write, doing backtrack. Okay, I'm going to write the nodes step by step. Okay, once I get all these nodes, then I'm going to reverse them. 11, 9, 4, 5, 1. Okay, and once I reverse them, then I'm going to make pairs. Okay, one is this pair, then next is this pair, then next is this pair, and then next is this pair. Okay, so this is what I'm going to do. Okay, so we are going to use the DFS traversal here. Okay, post order DFS traversal. Okay, so that we don't visit already visited nodes. And here if you see, I'm going to all the vertices one time, and I'm going to all the edges one time, right? So my time complexity is going to be v plus e for this specific problem. Okay, so that is why I'm using post order DFS. Okay, so now I'm going to write the code for this one. Okay, so let's move the coding part. Okay, so here what you need to do here, first create one map, integer dq integer integer, and here you can give adjacency matrix. Okay, new hash map. All right, and then we are just going to calculate the in degrees and out degrees. Okay, so this is a case where it's a undirected graph. Okay, and this is a case, in our case it's a directed graph. Okay, I'm taking undirected graph. Okay, so here that's why I'm checking in degree and out degree. Okay, not directly degrees. Okay, total count, but checking in degree and out degree. Okay, this is what I'm checking, right? And we have given this condition, there exists a valid arrangement of pairs. Okay, that is why I'm directly applying this. Okay, otherwise it will give some issue if there is some different type of example. Okay, but in our case there is always going to be a valid arrangement, okay, given to us, so we can easily apply this Eulerian path. Okay, so that's the only reason I'm doing that. Map, it is just like a game, right? You play this game, right? You want to uh, make a cube or something, but you don't need to pick up the pencil. Okay, if you are starting here, then you have to move further. Okay, until like this. Okay, you can't move cross a line again. Okay, that's nothing but Eulerian path. Okay, something like that. We are going to visit all edges only once, right? And then integer in degree is equal to new hash map. Okay, and now we are just going to write out degree. Okay, so now we are just going to build the adjacency list and track in degrees and out degrees. Okay, so here for int pair in my pairs. Okay, so now what I'm going to do here, start start is going to be pair of 0, okay, and end is equal to pair of 1. All right, and then now take this adjacency matrix, okay, and paste it. Okay, so here I'm just going to check compute if absent. Okay, so if this key start is absent, then create a new array DQ for that, this one, new array DQ for this one. Okay, and okay, it if it is absent, then it is going to create array DQ, otherwise it is already there. Okay, this DQ, so in that only just add the end value. Okay, add end. All right, and now we are just going to calculate the out degree and in degree as well. So out degree dot put. All right, so here start and out degree dot get or default start 0 plus 1. Okay, and same way we have to calculate the in degree as well. Okay, so let me just copy this line, paste it here, and now instead of out here I'm just going to write in degree dot put, and in place of start let's just write end. Okay, and here in degree dot get or default, here instead of start again write end. Okay, so I'm just calculating the start degree and end degree. Okay, and once I'm done with this, okay, then after that let's create a result array list. Okay, list of integer type, let's name it as result, is equal to new array list. All right, and then we have to find the start node. Okay, out degree should be equal to in degree plus 1. Okay, so initially let's do one thing, take my start node as is equal to -1. Okay, so if we know that there is always a valid arrangement of pairs. Okay, so if we are not able to find this, okay, then you can start from anywhere. Okay, then you can start from any vertex. Okay, because we know that valid arrangement is there. That's the simple meaning of this one. Okay, that's why I'm saying that. Okay, otherwise we are not going to start. But here in the problem statement itself is given that valid arrangement is there, so you definitely you have to start from somewhere. But if this condition is not satisfied, out degree is going to degree possible, then start from anywhere. That simply means that we can start from anywhere. Okay, so here for int node out degree key set. Okay, okay, so here if out degree dot get node, okay, if it is equal to in degree dot get or default node comma 0 plus 1. Okay, then in that case take start node is equal to node and break. Okay, if we find any start node then take that, otherwise just break. Okay, this is done. All right, now here this ends. Okay, now we have to start the DFS traversal. Okay, so simply I'm just going to visit. Okay, so you know that in DFS I'm just going to start from somewhere and then visit all the edges and then write it. Okay, so here I'm just going to simply call one visit method, and in this visit method I'm just going to pass my start node. Okay, I'm going to pass adjacency matrix. Okay, and I'm just going to pass result. Okay, this is done, and then we have to reverse the result since DFS gives us the path in reverse. Okay, so here I'm just going to write collections dot reverse result. Okay, and then we have to construct the result pairs. Okay, int paired result is equal to new int result dot size -1 by 2. Okay, size is this one, right? All right, now for int I is equal to 1, I is less than result dot size I plus plus. Okay, and here just we are going to add the values to my pair result, create the result I -1. Okay, is equal to new int. Okay, and here inside this I'm just going to write result dot get the element at I-1 index. Okay, two values I'm going to pass now. Result here dot get I. Okay, right, this is done. Okay, so now once this is done, so we are just simply, this is where my for loop ends, and here I'm just going to simply return paired results. Okay, that's it, that's what we need to do, paired results. Okay, and now in the end just write this visit. Okay, this is going to be very simple for you guys. Okay, so here private void visit int node map integer dq. Okay, and here in this dq integer. All right, and here its name is adjacency matrix. Okay, and what are the other things that we are passing? Result passing. Okay, so you can write here list of integer of result. Okay, so one second here, yeah, just copy this now, list of integer of result. Okay, so this is what I'm passing, and here inside this what we are going to do, first dq. Okay, and here integer neighbors. Okay, I'm just going to write any, actually let me write full neighbors. Okay, and adjacency matrix, matrix. Okay, dot get node. All right, okay, now after that just going to run one while loop, and in the while loop I'm just going to check neighbors while neighbors is not equal to null. Okay, this condition, and neighbors is not empty. Okay, all right. So for this condition I'm just simply going to first take the next node. Okay, I'm just going to poll it. Okay, I want to remove the connections, right? So into next node is equal to neighbors dot poll first. I don't want to visit again and again. Okay, so remove the connections again. Okay, and then after that just call this again and again. We are doing that. We are going to visit the neighbors, and instead of start node you can write next node. Okay, here next node. All right, and this is done here. Okay, we have written like this. Okay, and once okay we visit. Okay, and once this ends, okay, then we are just going to add the nodes. Okay, and by default they are going to add it in reverse order. Okay, because we are first visiting all the edges. Okay, so now let's run it and see if there are code issues. We'll try to fix that. So yes, there are some issues. So here appeared okay spelling mistake. Let's run it again. Okay, so here visit next node, or this. Okay, here I have to write adj matrix. Now spelling I'm taking that. Okay, adj matrix. All right, result, and here instead of result pass it result res I'm taking. Okay, I'm taking res here. I'm taking this. Okay, let's run it again. So there is some issue with the second test case. Okay, so let's try to fix that. I'm getting empty. Okay, let's see the reason. Okay, so here we are taking this. Okay, we are pasting over the pairs as well. I'm missing anything? I think so. Okay, okay, we have missed one line. Okay, so here I was saying that if this start node is not updated, okay, anywhere, if start node remains -1 only. Okay, so here okay, what is this? Okay, first let me just write that line. Okay, then I will explain. Okay, so if no such node exists, we have to start from the first pair's first element. Okay, so here if start node is equal to -1, then in that case simply update my start node is equal to pairs of 0 by 0. Okay, so let's run it again. So see, all the test cases has been accepted. Okay, so now see here. Okay, this is good. So now you will understand one more line. 1 3 3 2 and 2 1. Okay, 1 2 3 3 2 2 3 2 2 and then 2 2 1. Okay, so there is one cycle here. 2 2 1 2 2 1. Okay, so here if you see carefully, in degree and out degree, so in degree and out degree 1 1, in degree out degree 1 1, in degree out degree 1 1. Okay, so this condition is not satisfied. Okay, but we know that there are going to be valid arrangements, so you can start from anywhere. Okay, so I'm saying that let's start from first one only, this 1 3. Okay, start from here here here, that's it. That's a simple meaning. Okay, now let's submit it. So see, our solution is accepted and we have completed the November challenge as well, right? So I hope that you guys are able to understand today's problem. If you guys still have any doubts, then please feel free to ask in comment section. Till then, keep coding and keep practicing. Meet you guys in the next video. Thank you. Bye bye.